Imagine a robot. You're probably picturing metal, wires and flashing lights, right? But what if I told you that robots are becoming softer, more flexible, and even color-changing? This isn't science fiction. This is the exciting world of soft robotics, where material science and engineering combine to create robots that mimic the incredible adaptability of living organisms. Traditional robots, with their rigid bodies and jerky movements, are great for factories, but struggle in unpredictable environments. Soft robots, on the other hand, are designed to bend, twist, and squeeze into tight spaces, making them perfect for exploring the ocean floor, navigating delicate surgical procedures, or even interacting safely with humans. But how do these robots work? The secret lies in a fascinating field called mechanochemistry. Imagine materials that change their chemical properties in response to mechanical force. That's mechanochemistry in action. By using these special mechanochemically active materials, scientists are creating soft robots that can change shape, color, and even self-regulate their behavior. Let's dive into this world of squishy, smart machines and explore the materials that make them tick. You'll be amazed by what you discover. We are used to thinking of chemistry as something that happens in a lab, involving bubbling beakers and colorful liquids. But mechanochemistry takes chemistry out of the lab and into the realm of motion and force. It's the science of how mechanical energy, like pushing, pulling, or twisting, can trigger chemical reactions within a material. Imagine stretching a rubber band. You're applying mechanical energy, and the rubber band changes shape. Now, imagine that same stretching action, causing the rubber band to change color, or even glow in the dark. That's the kind of amazing transformation that mechanochemistry makes possible. In the world of soft robots, mechanochemistry is the key to creating machines that can sense and respond to their environment in remarkable ways. By incorporating materials that change their properties in response to mechanical stress, scientists are building robots that can adapt to their surroundings, heal themselves, and even perform complex tasks autonomously. So buckle up, because we're about to explore the fascinating materials that give these robots their almost magical abilities. Meet PDMS, or polydimethylsiloxane, the superstar material of soft robotics. Imagine a material as stretchy as a rubber band, as clear as glass, and as chemically inert as a rock. That's PDMS. This incredibly versatile material is a polymer, meaning it's made up of long chains of repeating molecules. It's this unique structure that gives PDMs its remarkable properties. PDMS is biocompatible, meaning it plays nicely with living tissues, making it ideal for medical applications. In soft robotics, PDMS is often used as the body of the robot. Think of it as the robot's skin and muscles. Its flexibility allows the robot to move and deform in countless ways, while its transparency allows engineers to see the inner workings of the robot in action. But PDMS isn't just a pretty face, or should we say body. It can also be easily modified with other materials to give it new and exciting properties. And that's where our next intriguing ingredient comes in: spiropyran. Section 4. Spiropyran, the Chameleon Chemical. If PDMS is the body of a soft robot, then spiropyran is its color-changing skin. Spiropyran is a type of molecule known as a photochromic compound, which means it changes color when exposed to light. Imagine a chameleon that changes color, not to blend in, but because it's exposed to sunlight. But here's the really cool part. When spiropyran is embedded within PDMs, it doesn't just change color with light, it also responds to mechanical force. Squeeze a piece of spiropyran-infused PDMs and watch as it changes color before your eyes. This incredible property opens up a world of possibilities for creating soft robots that can signal their movements, sense their environment, and even camouflage themselves. Imagine a soft robot exploring the ocean floor, changing color to match the surrounding coral and becoming practically invisible to predators. Or picture a surgical robot that changes color to indicate the amount of pressure it's applying to delicate tissues. The possibilities are as vast as the colors of the rainbow. Section 5. Mechanical energy to chemical reactions, a transformation. We've met our star players, PDMs and spiropyran. Now let's see how they work together to transform mechanical energy into a chemical response. Imagine a soft robot made of PDMs embedded with spiropyran. When this robot encounters an obstacle, it deforms, putting stress on the PDMS material. This mechanical stress alters the molecular structure of the embedded spiropyran, causing it to absorb different wavelengths of light and change color. In essence, the robot feels the pressure and expresses it through a visible color change. This is just one example of how mechanical energy can be harnessed to trigger a chemical reaction in a soft robot, but it doesn't stop there. By carefully selecting the types and arrangements of mechanochemically active materials, scientists can create soft robots that respond to a wide range of stimuli, including temperature, pH, and even specific chemicals. These robots can then be programmed to perform a variety of tasks, from gripping and manipulating objects to navigating complex environments. The future of robotics is soft, smart, and incredibly responsive. And it's all thanks to the magic of mechanochemistry.